Hello, I would like to thank the organizer to have brought us together in this conference and to have provided me the opportunity to present you today the automatic generation of C++ Julia bindings. I will start with a few words on the use case. I'm a particle physicist working in a large experiment, and we are using teras of CPU seconds to analyze tens of petabytes of data. The high-performance, high-level duality of Julia makes it the ideal language for particle physics, also known as high-energy physics, or HEP. And this is the reason why I'm here today with you. Nevertheless, we have a large legacy of code, mainly written in C++, and the adoption of Julia in our field can happen only if we can interface to this existing code. So this brings me to the project whose result I will present you today. The goal of this project is to demonstrate that Julia bindings can be provided to large C++ library in an automatized manner and with little maintenance effort. We need to fulfill a few requirements. First, the bindings need to be transparent to the Julia user in the sense that calling a C++ method or C++ function should be similar as calling a Julia method. Also, instantiating a C++ class should be similar as instantiating a Julia struct, and this is illustrated in the example given on the slide. We need to support large library with thousands of classes and methods, and adding bindings to an existing C++ library, including updating them when the library code evolves, should require the minimal efforts. This implies that types and methods to bind should be discovered automatically. Nevertheless, requiring a compilation step is not a limit for our use case. So what are the available tools to provide Julia binding to C++? First, we have the CXX package, which supports recent Julia releases, and I will come back to this package in the next slide. Secondly, we have the CXX package that provides direct access to C++ from Julia. In practice, we still need to write wrappers in Julia to provide a friendly interface to C++ library and reach the transparency that I was mentioning in the previous slides. Unfortunately, this package is limited to all Julia releases from 1.1x to 1.3x. So the project I will discuss you today is based on the CXX package. So with this package, in order to provide bindings to a C++ library, you need to implement a shell library in C++ where you declare the types and functions to bind, and this is what I will call the gluing code, and I will show you an example of this code in the next slides. Behind the scenes, the shell library wraps the C++ function and method in C functions, and then you use a Julia built-in C-call mechanism to access to the C++ functions. The package provides dynamically the Julia wrappers and reach the transparency that we have in our requirements. So here is the example of the gluing code. You need one line for each class to bind and one line for each method of each class to bind. You may need some additional line of code, but in general the code is quite simple. Nevertheless, it can be cumbersome to write and maintain if you have large libraries with thousands of functions and classes. So this gives us the idea to generate this code automatically, and this is the purpose of the rapid tools that we have developed. So this tool will produce the gluing code starting from the library header files. It requires the minimum configurations. The challenges in the development of this tool is that we need to interpret the C++ header files that are written in a sophisticated language. So the C++ standard takes almost 2,000 pages to be described. Another piece of challenge is that the header files are never done to describe an API, which is actually what we would have needed. We made the following design choice to develop these tools. First, we are using C++, and we are using the LLVM CLang framework. In particular, we are using its C API, which is called libclang. We are also doing few calls to its C++ API in order to have access to some features that were missing in the libclang. So before showing you how this rapid tool works, I will list you the features of this tool. So first, it extracts the list of classes and functions to wrap from a provided set of header files. So this has this has to be just a header files of library. You don't need to write specific header files, and you don't need to write the specific descriptions of the function and classes you want to bind. The lists, nevertheless, the list can be fine-tuned by providing an exclusion list where you can list the function and method that you don't want to bind. The tool will add automatically to this list all the types that are required to use the bind functions. That is to say, the types of the argument and of the return value of the functions, in case they are missing from the list. It maps the inheritance, so the C++ inheritance to Julia inheritance, so you are limited to one inheritance in Julia, so you can select which parents will be mapped in the Julia code. It can also generate accessor for the class fields, and this is interesting because the CXS wrap does not provide access to the field of the classes. So I will show you how this works on the demonstrations. So for this, I will use a use case of a legacy library that we want to interface to Julia. This library is a root, is a data analysis framework which is used in most of the high energy physics publications. This framework was developed to analyze petabytes of data produced at the Large Hadron Collider at CERN. It includes a C++ interpreter with JIT compilations, a Python interface. It supports Jupyter, including C++ kernel. Here, it provides data frames that are designed for large datasets, a data file format also optimized for large dataset, and more. But one thing which is missing from the list is the Julia interface. This framework includes all the tools that are used in health data analysis, including histogramming, fitting, machine learning, data unfolding, plotting, and more. It results in a large library that exports more than 8,000 C++ classes. So in the help analysis, we do a statistical analysis of physics events. A physics event is a measurement of a collisions, and it corresponds to a statistical event in the analysis. So on the right, you have a display of physics events. So here we collide two protons, and from the collisions, many particles are produced, and in yellow, this is the tracks of the produced particle. We are producing billions of those events, and we need to analyze these events. And in the help analysis, we make a wide use of histograms, and this works in two steps. In the first step, we loop on this billion of events, and we fill the histograms, and it results of this step, a data reductions, and then we use the histogram to analyze them and to plot, and to do the plots. Before coming to the root example, I'll start with a simpler example. So imagine that you have the following class that has a constructor which takes one argument with a default value, world, and stores the value of this argument in a field, which is a string. The class has also a method, hello, that will use this argument to display some message. So this class uses IOString for the display and the string library for the character string. So in order to provide a binding for this class, we need to write a configuration file, and we'll see that this configuration file is simple. So you need to provide the name that you want to give to your Julia module, the list of header files that contain the classes to bind. Well, here we have only one header files. The list of directories where this include files can be found, and finally the C++ standard to be used to interpret your header files. So now that we have configuration files, we can run the rapid tools. So we provide the configuration files on the command line. So he has produced the wrapping of one class and two methods. So the two methods are the constructor and the hello method. So let's see what has been produced. So we have a header file that has been produced, a CXX file, which is our gluing code, and the Julia file that defines the Julia module. So we can have a look at the C++ code which was generated. So here we recognize the item method that I mentioned in my slides, which is used to declare the binding of the class A. We have also a call of constructor method, which is used to request binding of the constructor. Here we have two because we have one for when we are using the passing an argument, and one when we are using the default value of the argument. And we see the method that was I've shown also in my slide, which is used to ask for binding of the method of the class. So now that we have this code which has been generated, we can compile it. We just do make. So we compile this exist file in an object and then build this object in a shared library. So now we have the shared library. We can use it from Julia. Before, I will source a setup file which we just add the current directory to the load path of Julia and to the LD library path, as you can see from the file. So here's the content of the file, of this source file. So now I start Julia. I will import the Julia module we have created. So we had one class which was called A, so we can create an instance of this class. As if I was creating an instance of a Julia struct, so hello.a, it was taking one argument, so let's give some value to this argument. So we have this instance, and now we can call a method of this class, so the sayHello method. In C++, it will be a.sayHello or a_sayHello, and in Julia, it becomes sayHello of a, so this parameter becomes the first argument of the Julia method, so sayHello a, and then it just calls the C++ shared library and print out the expected message. So, hello Julia's aficionados. We have seen that the constructor has a default value for this argument, so we can also create an instance without providing any values. And we can call the method with this argument, with this new instance. And here you just use the default value. So this is something which is added by Rapid to the CXS wrap, which does not support by itself the default value of functions arguments. So now that we have seen this simple example, we can move to the more complex example of the roots. So it is this package that we want to provide binding for Julia. So here we will not provide binding for the full package. So you remember 8,000 lab classes. We are not yet able to do this, but just for a subset of classes, so 63 classes of this project. So now, so we have also a configuration file, so we can run Rapid. I will show you later what this file contains. Would generate it up. So it runs on it. And he has generated 63 classes, also wrapping for enums, 1,593 methods, and also some accessor and some global functions. So let's see the code he has produced, the files that he has produced. So we still have our header files, the Julia method, so here is larger because it includes the export of many methods, and the C++ code, so you see it's quite large, 747 kilobytes. Yes, 11,000 lines, and we can count also the C++ statement by counting semicolon. 5,000 C++ statements. So here you understand what I meant by cumbersome to write the wrapper by hand. We can look at the file. So this isMirror type is just to specify that the class contains method, and it's not a trivial struct. We have the add type that we have seen in the hello world example. So it is called for each method, for each class, sorry. And for each class, we are calling a constructor for the class constructor and the method for each method of this class. So now that we have this code which is generated, we can compile it. So I will just show you that it takes some time. So in the meantime, I will show you what the configuration file takes. So it's also quite simple. So we have the name that we want to give to the Julia module. The include dirs, which here now is the include dir of the installation of this root framework we want to provide the bindings to. A list of the header files where the classes to bind can be found, and also a list of extra header files where the tools can find types that are needed to call the bound functions and that are not in the header files containing the classes to bind. I mentioned you that we can exclude some methods and classes from the binding, and for this we provide a file and use this veto list parameter to pass this file. We have the C++ standard, and for the inheritance, in case of multiple inheritance in C++, we can specify the parents that we'll use in Julia. The syntax is a child colon parent. We can also disable the mapping of inheritance, which is done here. So to do this, we just give an empty string for the parents. And finally, we can exclude some symbol from the export lists in order to avoid name clashes. And note that we have also different mode of exports. We can also ask to not export any symbol, and we can also add to export more symbol. That's just the method of classes. So now the compilation is done. Now that it is compiled, we can use it. So we need to source the setup file as before. And now we start Julia. Import the module. So I will import another module which is running the event loop of the graphical user interface of root, because here in this example I will use graphics from the root framework. So this package is at root, so it's using itself the root package. So I told you that in the help analysis we are doing a heavy use of histograms, so I will create an histogram. So this is supported by the th1d class of the root framework. Its constructor takes a name for the histogram as argument, a title of the histogram, a number of bins, and bounds for the x-axis. So here I will not loop on the physics event. I will just fill the histogram with random numbers. For this I can use a method from the th1d class, which is called fillRandom. So in C++ it will be h arrow fillRandom, in Julia is fillRandom of h. The method needs a name for the distribution to use to draw the numbers. And we can also tell the number of events that we want to generate. Okay, so now that we have this histogram, we can draw it. Sometimes we need to call it twice. And so here is the histogram which has been filled with random number. So now I told you that we have also fitting tools. So the th1d has a fit method. So I can call it. So fit h. So here I don't need to mention the module because by default the methods of the class are exported. And I will fit with the Gaussian. So we should get a mean of 0 because it's the default of the field random, and of sigma of 1, which is the case. So if I refresh the plot, we see the functions which perfectly fit with our histograms. I mentioned you that the root framework has a format to store objects. So it gives me the opportunity to show you that we can do I/O with an external C++ class. So I will create a file. Here I need to call a static method, and the rapid maps the column of C++ in exclamation mark. So I use exclamation mark in place of column, and the function is open. I must give a name for the file and an opening mode, which is recreate. Now that the file is open, I can write the histogram in the file. For this I use the write method of the th1d class. So write h. Now that the histogram is written in the file, I can exit from Julia, and I will check that the file has been created. It is here, and I will check the content of the file from the plain root tools. So I just write root demo. Demo.root. I can list the content of the file, and I see I have one object of type th1d. I can draw this histogram, and I mentioned you that root as a C++ interpreter, so I will use C++. So this is the draw of h that I've written in Julia, which in C++ is h draw. And here we see that we have in this file the histogram that we have created. We have also the fitted functions, because the fit method of th1d stores the result of the fit inside the th1d class. So we have seen that with very few lines of configurations, we can provide the bindings of thousands of methods. Nevertheless, these tools have some limitations, which are the following. The first limitation is that the generated code is grouped into a single file, which can be large and long to compile. And this is our current bottleneck for large library. A version that produces one file per class is under development and should be available soon. Therefore, this point is not a showstopper. The second limitation is class template support is partial only. We don't have yet support for function templates. Now, here for the class templates, we are facing limits of libclang. Namely, we miss the parsing of template specialization abstract syntax tree. So to overcome this problem, we need to either switch to the C++ API of clang, namely lib2link, or to have this parsing support added to libclang. The third limitation is that the inheritance mapping is limited to one parent, but it should be easy to extend wrap it in order to generate wrappers for all methods inherited from any parents. It means that we'll map the C++ polymorphism to Julia dispatching. We should note that mapped type relationship will remain a single inheritance as is a concept from the Julia language, but this is a minor limitation. So the outcome of this study is that the automatic generation of C++ library bindings is possible and is not difficult to implement despite the complexity of C++ language, and this thanks to the clang library. We should note that help and documentation could also be generated automatically since the clang provides support to pass docstrings. So now it's time to sum up. I have presented you a prototype which was developed to test automatic generation of Julia bindings for C++ based on CXS wrap. With this prototype, we have demonstrated the feasibility of such automation. The prototype is well advanced. More development is needed to leverage the prototype to production tools that will fully support the C++ templates. I hope that you enjoyed these presentations, and I will be happy now to answer to your questions.